Okay, so get ready for a wild ride today because we are diving headfirst into the seriously mind-blowing world of particle physics.
Sounds exciting.
Yeah.
And you've chosen some really thought-provoking research for us to explore. This paper about beyond the standard model physics and the potential of these LHC upgrades has so much to unpack.
It does. It's a pretty dense paper, but it's full of these tantalizing possibilities. Like, okay, we know the standard model of particle physics has been amazingly successful explaining so much, but it just can't be the whole story, right?
You're right, it can't be the end of the story. Think of it this way. The standard model is like a map of a continent. We've gotten pretty good at navigating the coastlines, the major rivers, the big cities, the landmarks. But there are these vast, uncharted territories just waiting to be explored. And those are the areas where things could get really interesting.
Okay, I like that, the map analogy. So where do we even begin to explore on this map? What are some of the big unanswered questions this research is trying to tackle?
Well, one of the most perplexing mysteries is something called the hierarchy problem.
The hierarchy problem.
Yes, it really boils down to this question of balance, or rather a lack of balance. You see, the Higgs boson, that particle responsible for giving other particles mass, should theoretically be much heavier than we observe.
Wait, hold on. Something is messing with the Higgs boson's weight? Is there like a cosmic diet plan we don't know about?
Haha, not quite a diet plan. But you're right, something must be influencing it. The current standard model just doesn't have a good explanation for why the Higgs mass is so relatively small. It's a bit like, how can I explain this? It's like trying to balance a bowling ball on top of a pinhead. The math just doesn't quite make sense.
So what are physicists proposing to explain this? Are we talking about like invisible cosmic bowling ball tamers?
Huh. Not exactly, but it's good to think outside the box. Some of the most compelling theories trying to address the hierarchy problem and other mysteries actually revolve around ideas like supersymmetry, often shortened to SUPSY, and extra dimensions.
Okay, I've heard those terms thrown around before, SUSY and extra dimensions. I have to admit, they always make me think of, sci-fi movies a bit. How do those ideas actually fit into, like, real-world particle physics?
I get it, it's easy to see them as science fiction. But these are serious contenders in the realm of physics. Take supersymmetry, for example. It suggests that every known particle we've discovered actually has a hidden partner particle, a superpartner with different properties. These superpartners, they could be what's influencing the Higgs mass, what's solving this hierarchy problem.
So there's this whole hidden world of particles influencing the ones we can observe. It's like those secret societies in history, pulling the strings from the shadows.
That's a really great way to put it. And just like historians uncovering evidence of those secret societies, physicists are working hard to find clues of these hidden particles. That's where the Large Hadron Collider, the LHC, comes into play. It's currently our most powerful tool for smashing particles together at these incredible speeds, hoping to create conditions extreme enough to, just maybe, briefly glimpse these hidden partners.
Right, the LHC, I feel like we hear about that a lot. But this paper, it specifically focuses on upgrades to the LHC, correct? The HL-LHC and HE-LHC.
Exactly, because even the LHC, as powerful as it is, has its limits. The HL-LHC, that's high luminosity, will significantly increase the number of particle collisions. It's all about increasing the odds, giving us a better chance of seeing those rare events that might hold the answers we're looking for.
So more collisions, higher chance of seeing something groundbreaking.
Exactly. Think of it like casting a wider net to catch more fish.
Yeah.
And then there's the HE-LHC for high energy. It's designed to smash particles together at even greater energies, which could create heavier, more elusive particles that we haven't been able to see before.
Ah, okay, so it's like using a stronger fishing rod to reel in the bigger catch.
Precisely. And this paper goes deep on some of the specific catches we might find with these upgrades. One intriguing target, for example, is the gluino.
A gluino? Is that like
Yeah,
the superpower version of a gluon?
you got it. Gluons, they're the particles that carry the strong force, which is one of the fundamental forces of nature. Now, in supersymmetry, every particle has that partner particle, right? The gluino would be the partner to the gluon. And this paper suggests that the HL-LHC and HE-LHC might finally be powerful enough to produce and detect these gluinos.
Okay, so if you find these gluinos, would that be like a home run for supersymmetry? Would it change everything?
It would be huge EA.
Huh.
Remember the hierarchy problem we talked about? Finding gluinos would be a massive piece of that puzzle, potentially confirming supersymmetry and revolutionizing our understanding of the universe's fundamental building blocks. And it gets even more exciting.
Okay, so gluinos, supersymmetry, potentially rewriting physics. This is getting pretty intense. But how do you actually go about finding these gluinos? It's not like we can just, scoop them up with a tiny net,
Oh,
right?
you're right, it's a lot more complicated than that. Remember, these particles, if they exist, they'd be created in these incredibly high-energy collisions. And they'd be extremely short-lived, decaying almost instantly.
So by the time we even know to look for them, poof, they're gone.
Pretty much. So physicists have to become like detectives, looking for clues of their existence by carefully analyzing the debris from these collisions, the particles they decay into.
So it's kind of like forensic science, but on the subatomic scale, looking for those telltale signs.
Got it. And one of the key things they look for is missing energy. You see, this paper suggests that a gluino could decay into other particles, including something called the lightest supersymmetric particle, or LSP.
Okay, the LSP. What is that, and why is it important in the gluino hunt?
Well, the LSP is theorized to be neutral, meaning it wouldn't interact with the detectors at the LHC. So if a gluino decays, you'd have all these other particles spraying out that you can detect, but their total energy and momentum wouldn't add up. There'd be this apparent missing energy, hinting at the presence of the LSP, and by extension, the gluino that decayed into it.
Wow, that's incredibly clever. It's like, I don't know, deducing that someone stole a cookie from the cookie jar even though you didn't see them, just by noticing that there's one missing.
That's a great analogy. And this paper actually goes into a lot of detail about how the HL-LHC and HE-LHC could be used to detect gluinos through these missing energy signatures, even for gluinos much heavier than what we could currently observe.
That's fascinating. But gluinos aren't the only particles on the most wanted list for these upgraded colliders, right? I mean, this paper is called Beyond the Standard Model. What else are physicists hoping to find?
Oh, you're absolutely right. There's a whole buffet of potential discoveries laid out in this paper. For instance, there's a lot of discussion about charginos and neutralinos.
Okay, more intriguing names. Those sound like they're related to supersymmetry, too.
They are. These are hypothesized to be the superpartners of the particles that carry the weak force, the W and Z bosons, and even the Higgs boson itself.
So, like, gluinos finding charginos or neutralinos would be a pretty big deal for supersymmetry.
It would be huge GE. It would be like finding more pieces of that puzzle we're trying to put together. And the paper gets into some pretty complex scenarios, like what they call compressed CSY scenarios, where the mass difference between these particles is tiny, making them even harder to detect.
Because their energy signatures would be even fainter, right? Like trying to hear a whisper in a hurricane.
Exactly. But the authors seem optimistic that the increased sensitivity of the upgraded LHCs, that greater luminosity and energy, might be enough to finally give us a clear signal.
So we've got gluinos, charginos, neutralinos. This is a lot to keep track of. But there's one big, I guess you could say, elephant in the room that we haven't even talked about yet. Dark matter. We're talking about something that makes up the vast majority of the universe's mass, and yet we still have no idea what it is. Does this research offer any clues about dark matter?
It absolutely does. In fact, the search for dark matter is one of the most compelling reasons for building these upgraded colliders in the first place.
Okay, but how would these colliders help us find something that's, well, dark, something that doesn't interact with light?
It's the million-dollar question, right? Well, remember that missing energy signature we talked about with gluinos? That's actually one of the primary ways physicists hope to find evidence of dark matter particles.
Wait, so the same kind of signal that could point to a gluino could also point to dark matter, like a 2-for-1 deal?
Precisely. One of the leading ideas is that if dark matter particles are created in these high-energy collisions, they would just fly out of the detectors undetected, leaving a similar pattern of missing energy. They even have a specific name for these searches: monojet searches.
Monojet searches?
Yes, because often what they're looking for is a single jet of particles with a whole lot of missing energy in the opposite direction. Like something invisible just came along and gave that jet a good whack.
Wow. So we're talking about using these incredible machines to, in a sense, see something that's invisible.
In a way, yes. And the upgraded LHCs, with their increased sensitivity to these monojet events, could open up a whole new window into the potential properties of dark matter.
That is just amazing. It's like we're shining a light, not literally, of course, into the darkest corners of the universe.
It really is remarkable. But there's one more fascinating twist to this story that I think you'll find interesting.
Oh, yeah. You've definitely got my attention. What's this fascinating twist?
Well, we've been talking about the LHC like it's this giant superpowered microscope, right? But what if the things we're trying to see through that microscope are, well, a little bit blurry?
Blurry? What do you mean by blurry in this context?
What I mean is, some particles, they might not behave exactly as we expect. They might not decay immediately after they're created. Instead, they might travel a certain distance within the detector before transforming into other particles.
So they're kind of like those kids in a game of tag who run and hide before anyone can catch them. They're playing hide and seek inside the detector.
Exactly. These are called long-lived particles, or LLPs for short. And they present a unique challenge because their signatures in the detector, they're completely different from what we normally look for.
So how do you find something that's practically invisible, something that's deliberately trying to avoid detection? That seems like a tall order.
It is.
Mm.
And it requires a totally different approach, a different set of tools and strategies. But the authors of this paper seem confident that the HL-LHC and HE-LHC, they'll be up to the task.
Wow, this is incredible. We've gone from searching for missing energy to chasing after particles that are practically invisible. It really makes you wonder, what else is out there, hidden in plain sight, just waiting to be discovered?
That's the beauty of science, isn't it?
Yeah.
There's always something new to learn, more mysteries to unravel, and with these incredible tools at our disposal, who knows what secrets the universe might reveal next?
It's like we're explorers setting sail into uncharted waters. Except instead of a ship, we have these massive particle colliders. And instead of new continents, we're discovering new particles, new forces, maybe even new laws of physics.
I love that analogy. And just like those early explorers, we really have no idea what we might find. It's a truly thrilling time to be a physicist.
It really is. But it's not just about the excitement of discovery, right? This research has the potential to completely change our understanding of the universe, maybe even our place in it.
Absolutely. We've been talking about some pretty mind-boggling concepts today. Supersymmetry, extra dimensions, dark matter, these long-lived particles. If even a fraction of these theories turn out to be true, it would require a major shift in our understanding of physics.
So we're not just talking about adding a few footnotes to the textbooks, we're talking about potentially rewriting entire chapters, maybe even the whole book.
Exactly. Imagine if we discover that our universe is just one of many universes, all connected in ways we can barely comprehend. Or that there are hidden dimensions all around us, influencing our reality in ways we never even imagined.
It's like that moment in The Wizard of Oz when everything goes from black and white to color. Suddenly we're seeing the universe in a whole new light.
That's a perfect way to put it. And it's not just about the theoretical implications either. These discoveries could have profound practical applications as well, things that could change our everyday lives.
Right. I mean, history is full of examples where scientific breakthroughs that seemed purely theoretical at first ended up revolutionizing our world.
Exactly. Think about electricity. When Benjamin Franklin was flying his kite in a thunderstorm, he had no idea that his experiments would eventually lead to the power grid that powers our modern world. Or take quantum mechanics. It seemed like this abstract, almost esoteric theory a century ago, but now it forms the basis of the computers and smartphones we use every day.
So who knows what amazing new technologies might come out of this research in particle physics. We might discover new sources of energy or revolutionary new materials, maybe even finally crack the code of quantum computing.
The possibilities really are endless. But even more importantly, I think this research has the potential to answer some of humanity's biggest, most fundamental questions. What is the universe made of? How did it begin? And are we alone? These are questions that people have been asking for millennia.
It's like we're trying to read the universe's source code, line by line, particle by particle, and with each new discovery, we're getting a little bit closer to understanding the grand tapestry of reality.
Beautifully said. And that's what makes this field so captivating. It's not just about equations and experiments. It's about pushing the boundaries of human knowledge, exploring the deepest mysteries of existence.
This has been an absolutely mind-blowing journey. We've covered so much ground, from the limitations of the standard model to the search for these new particles, the mystery of dark matter, the strange world of long-lived particles. I feel like my brain is overflowing with new ideas.
Mine too. It's been a pleasure exploring these ideas with you.
The feeling is mutual. Thank you so much for taking us on this incredible deep dive. I can't wait to see what mysteries the universe reveals to us next.
The pleasure was all mine. And remember, the universe is full of wonders, just waiting for us to uncover them.